number 2, and this one continues on the next page. Okay, so here's what we do with that information that you learned how to find on number 1. We find all the possible zeros, and then what you do is you use synthetic division to find one of them that is actually a 0. So you just, here where they only had 2 possible zeros. If you look in the book, you'll see how they test all the different zeros, but anyway, 2 works. If you do synthetic division, you get a remainder of 0, which means that x minus 2 was a factor. So that was a theorem from 3.3. So what that tells you is a missing piece of the puzzle. That means that x minus 2 times what this would be is x squared plus 3x plus 1 equals 0 is another way to write this function. So it's factored now. So we know one of the zeros is 2. Now we need to set this factor equal to 0. And since this trinomial doesn't factor, we do the quadratic formula. And they come up with this. So our zeros are 2 and then these 2 real rational numbers. So these are all real zeros because we're going to get imaginaries here in a little bit. These are all real. Not rational. I started to misspeak there. That's not rational. But these are all real. So the pencil problem, you find all of your possible zeros doing the factors of -6. So these over the factors of 1. Okay, it's nice when that happens because then basically the possible rational zeros are just the ones in your numerator because we're just dividing by 1. So these are all of our possible rational zeros. If you try synthetic division with +1, it doesn't work. If you try it with -1, so I'm doing this. You get remainder of 0, so that means that x plus 1 is a factor. And so it'd be x plus 1 times x squared plus 3x minus 6 equals 0. So we've already got one of our zeros is -1. This does not factor, so we do quadratic formula, and you end up getting -3 plus or minus root 33 over 2. Number 3 is basically the same question. So if you look at their solved problem, we've got the factors of 13 over the factors of 1, and sorry, my cat just came in the kitchen. That's it. Okay. So they found the possible rational zeros, and then they tried +1. They found that remainder 0, so that works. Come on. And so the thing is, and your pencil problem isn't like this, but then they are left with a cubic, and so they try to nail down another factor out of that because we can't do quadratic formula on that. So they try 1 again, and they get remainder 0 again, which means that 1 is a root with a multiplicity of 2. So like x minus 1 squared is one of the factors with a multiplicity of 2 of this polynomial. And then that helps them get to this point so that it's x minus 1 squared times what was left here, x squared minus 4x plus 13. equals 0. And then they do quadratic formula on the rest of that. And so the roots are 1 and then 2 plus or minus 3i. So go ahead and pause this and try your pencil problem. Come on. Okay, so for the pencil problem, so you've got all these factors of 12 and then over the factors of 1, so plus or minus 1. Okay, so basically it's just all of these numbers that you'd want to try. So I always try 1 first. Okay, and lo and behold, we got remainder 0. So that means 1 is a root, which means x minus 1 is a factor. And then here's the rest of that, the remaining factor, x squared minus x minus 12 equals 0. So this is now what we're trying to solve. And if you look at this factors. You know what multiplies to negative 12 and adds to negative 1? Negative 4 and negative 3. So this is x minus 1 times x minus 4, sorry, and positive 3, x plus 3. So your zeros are 1, 4, and negative 3. Number 4. So if you look at this solved problem, it says find a third degree polynomial function with real coefficients that has negative 3 and I as zeros, such that f of 1 equals 8. Okay, so I want you to look straight to this line right here. If negative 3 is a 0, that means x plus 3 is a factor. If I is a 0, remember I told you earlier that the imaginary zeros always come in pairs. So then you're going to have x minus I and x plus I as zeros. Okay, so then what they do next is they multiply this out. So x minus I times x plus I is x squared minus I squared. Remember, I squared is negative 1, so that's actually x squared plus 1. Okay, so now they've got this, then they multiply that out to get this, and now we bring in this information, which is like what we did in that third warm-up. So we use f of 1 equals 8. Okay, so we, so here they're plugging in 8 for y and 1 for x and solving for an, and they get that an is 1. And then you put an back into the function. Now, since it's 1, they basically just removed the parentheses. If this had been like negative 1, you would distribute it. Okay, so try your pencil problem. Pause the video. Okay, so if we're given f of x, if we're given that we have I and 3i as zeros, that means, oops, first you got to write your an, and then it's x plus I, x minus I, x plus 3i, x minus 3i. Okay, so we multiply all that out. Remember, this is like multiplying a plus b times a minus b is always a squared minus b squared. That helps you do it faster. Okay, so this is x squared minus I squared, and this is x squared minus 9i squared, which is x squared plus 1 and x squared plus 9. So then you multiply that out, and you get x to the 4th plus 10x squared plus 9. Okay, remember this is all equal to f of x. So now we're going to set f of x equal to 20 and plug in negative 1 for x. So when I plug in negative 1, raise that to the 4th, I get 1. When I plug in -1 squared times 10, I get 10, and then plus 9. So we have this. So an is 1 again. So your final answer, you plug in 1 back in for an, so it's just x to the 4th plus 10x squared plus 9. And now I want to direct you back to this part of the beginning of your notes, Descartes' rule of signs. So you look at the number of sign changes in your polynomial, and the number of positive real zeros is always either going to be the same as the number of sign changes, or that number minus 2, and then minus 2, like until you get down to 0. This will make more sense, I think, when we do the example. And then the number of negative real zeros is always the number of sign changes, the same as the number of sign changes of f of negative x, or 2 less than that. So like if you had 4 sign changes, then it would be, you could either have 4 negative real zeros, 2 negative real zeros, or 0 negative real zeros. So look now at example 5. Okay, so here, let's look at the sign changes. So here's the first sign change, because this is positive x to the 4th, and then now it's negative 14x cubed. So that's one sign change, second sign change, third sign change, fourth sign change. So f of x has 4 sign changes. So that means it either has 4, 2, or 0 positive real zeros. If it had had 6 sign changes, it would have 6, 4, 2, or 0 positive real zeros. Okay, then for the negative real zeros, you find f of negative x. So see how here they find f of negative x, and that has no sign changes. So that means f of x has 0 negative real zeros. So pause and try your pencil problem. So you notice that f of x has no sign changes. So that's no positive real zeros. So then we find f of negative x. So plug in negative x for each of these x's. So that's going to become this. And so this has 1, 2, 3 sign changes. So that means that f of x either has 3 or 1 negative real zeros.